So hello and welcome to week 3 of our book club, where we're meeting to cover the book Programming Quantum Computers. If you've missed previous weeks, we have these posted up on YouTube. What we are doing is working through this book. We've got a group of interested people, none of whom have brought quantum experience. We're all learning together. And this week, we're really fortunate in that Jared has offered to lead us in our discussion of chapter 3. So without further ado, I'm going to turn it over to him and really thank him again for stepping up to lead. If anybody else wants to lead subsequent weeks, we'll talk about it at the end of this week. So go ahead.
Share screen. Thank you, everyone. Thank you for this wonderful opportunity. This is something that I really enjoyed, although I will say that while doing the research and the studying, it wasn't quite enjoyable, but I'm very eager to share how my mind was able to comprehend information. And also, I'm looking forward to, at each portion of the presentation, also opening up to the public, especially when it comes to the operation, and see how we can find logic to this. Okay. First, so last week, Jeremy presented operations, and it was an amazing thing to see how how those operations go through those qubits. Now, this week, we are actually doing operations, but with multi-qubit registers. So first, we're going to go through a circle notation for multi-qubit registers. And throughout our experiments in coding and programming, we'll introduce entanglement, a phenomenon that most of you know of. But instead of actually giving it a nature, we are going to see it in action as a program. We're also going to draw a multi-qubit register, a little bit different than a circle notation, then delve into single qubit operations, had, not, and phase, and then finish with multiple qubit operation, C phase, C not, and of course, CC not. And without further ado, let's start. Okay, great. So for the circle notation, okay, great. So for the circle notation, what we have for one qubit, we normally see the familiar 0 and 1, as you can see here. But for what I understand, when it comes to multiple qubit, especially in the same register, it's the key for the circle notation. It's 2 power to n. Is that how you say it in English? Power to n? Yes, 2 power to n. Meaning, if you have 2 qubits, it's 2 power to 2. So for a circle. Also, as far as 3 qubits, 2 power to 3, which would bring us to 8 circles. And as you know, this is not really one per circle per qubit. It's more, for what I understand, it's more of one circle for each 2-bit number that you can get when you do a read. So it's the idea that each of these represents the possibility of a 0 over 1 over those circles. And again, this for me brings us back to the idea that probability is so important. In fact, I think it reigns supreme when it comes to the world of quantum computing. Something else that is very important when it comes to the notations, here you get to see the shaded area. At times, the shaded area can be smaller or wider, and it represents the magnitude, which is the probability that the specific value will be observed when the qubits are read. And of course, another aspect which we're going to study are those lines, which I believe represents the phase, which are for the purpose of today's presentation, we can just call them like the angles. Okay. Continue. Now, as we draw multi-qubit register, you'll notice that the circle notation employed a 2n system, meaning, again, 3 qubits, it's 2n, 6. Now, when it comes to drawing the multi-qubit register, as opposed to the qubit notation, it's a matter of adding a label, which is equivalent to the binary value. So 1 qubit would be 0 multiplied by 1, 2 qubits, 0 multiplied by 2, 4, 8, and you go down the line. And we are going to see the multi-qubit register as we go through the programming, especially when we use the O'Reilly JavaScript and QSAM system as well. Okay. Okay, again, here I wanted to give a different perspective of two multi-qubit quantum circuits, where you have the first register with 4 qubits registered to it, and the second register, which will anchor after the first one, having 2 qubits. And for that, I also have a code ready for you. Let me start. So at first, we always start by setting QC, setting the amount of qubits that we are going to use. And in this notation, we use the QC reset. Now, something we can also do is somewhat set the qubits that we have to 0. So let's write to 0. Now, the first thing we can do is create a register. And how you create a register is with JavaScript, which is one of my favorite languages, is you create a variable, let's call it reg1, and then the operation for that programmatically is qint.new. The first thing you do, you add the amount of qubit that you want to assign to this register. Let's just say for this register, we just want 1 qubit. And here you get to name this register. Let's call this register, not JSpice. Let's call it register 1. You know what? Let's do Gerard 1. And then let's call the second one and this is an homage to a gentleman who's been very kind to me. We are going to call this one J2. Homage to Jeremy. So here we have 2 registers. The first one, as you can tell, the first one only has 1 qubit associated with it. The second one, 2 qubits. Now, if we were to run this program, so far this is what we see. We have 3 qubits. The first qubit is assigned to Gerard, the register Gerard 1. The second and third qubits are assigned to the second register. And you can tell here they are set to 0 for the moment. And again, something we can also do is just for some quantum magic, we can either put all of our qubits into superposition by doing QC had, all of them will be in superposition, as you can tell here. And again, here you see the magnitude. The magnitude somewhat becomes almost the same here as a way to show the probability of getting a 1. Or instead of that, we can only have 1 register in superposition. For example, we could have, I believe, reg1 had perfect. Oh, yeah. Okay. Yes, reg1 is in had, or reg2 could be in superposition. Now, there are many cases where 1 register or even 1 a qubit in a register could be in the superposition. For example, later on in this presentation, we are going to see the bell curves. What is it about? The bell pairs. It's in a situation where you have one qubit in superposition. No, one register in superposition, the other one not. And we'll be able to explore that later. So right now, this is the register rotation of the register. This is how the multiple qubit register, this is how it's, you can see it here. Here we have the circle notation sign there. Perfect. And as you can see, 0, 1, the register that has 2 qubits follows the binary label next to it. Now, just to play around, let's set 6 qubits. And then let's assign Jeremy's qubit 5. Now, Jeremy's register 5 qubits. As you can see here, you have this, but you also have the amount of circle amounting to that. Now, if you go here and you create a had, you'll be able to see this. Can I continue, team?
I have a question.
Yes, please.
So, is it on purpose or a deficiency that the registers are combined into a single circle notation? Because it seems like to me it would be easier if they were separate, but maybe there's a reason they're not.
You know, we will see in a couple more examples. We'll see specific situations where qubits in one register actually interact in a certain way, and qubit in different registers interact in different ways. I apologize. So, yeah. You know,
yeah, I totally get that they interact, but what gets me is that there's only one circle notation representation. So like we're looking at the J2 register and everything is zeros, but Gerard 1 is a 1, then it shows a 1, but you really just want to know the value of J2, which is 0. But the Gerard 1 screws everything up, you know? So that's what was kind of confusing me.
I have the exact same. I had a very similar question, which is, does a register actually exist? Because there are qubits and they're represented, but it looks to me like my resolution was the QC engine decided to call something a register by grouping some of them, but it had no qubit meaning. There's no mathematical meaning except you can apply an operation to everything in the register. So it's syntactic sugar to address multiple qubits when you operate them, apply.
So first of all, I will say kudos to that expression, syntactic sugar. I love that. I do think there is something to be said by using registers. For example, here, we can read a register. Let's just try right now. Let's say we're reading Reg 2 and reading Reg 1. What would happen? Let's say we were to read both of them. Interestingly here, we're getting an interesting case where you have one qubit here being read as a 1. Let's do it again. The one thing that's not changing is this one, and we all know why. In case we don't know why, it's just this idea that if it's not in superposition, it's not in this state of limbo where it's allowed to change its nature. Now, let's say if we're to put Gerard 1 into superposition, Reg 1 had, sorry, Control S. Here you get a chance. There's a probability, I would say 50% chance that Gerard 1, this register, becomes a 1. Now, if there's something we have to also understand, there's no entanglement right now. So both qubits, they're not entangled. So there's nothing that links them in terms of when you read them, and they will become almost similar, like from a probability standpoint. So you have instances where you're running this and they're showing different values. So here, that's one instance where I can see where having a register and holding qubits inside that register actually does something. But the interesting part is we're just getting started. This is just the third chapter, and we are going to get into entanglement. And you have to hold me to the idea that when we get to a point where having multiple registers being entangled, whether by doing some like a C naught or a C phase, then we can check, we can do the same thing. We can read and see how they're changing. I'm aware that I'm not answering the question, but hopefully I'm giving a sense of interest. Thank you very much, Daniel, and thank you, Nuri. Okay, that being said, if you don't mind, let's continue.
Jared, I have a question for you.
Please do.
I don't have a software engineering background. Like I picked up data science, but I've never worked with JavaScript. What is a register? Is that just a way of holding things together? Is it like a container for something? I'd love to get your perspective on that because I'm not familiar with them.
And I appreciate this. My perspective, actually, in terms of syntax, I don't know if JavaScript has a register as, that it is part of the JavaScript language. The register, from my perspective, is a container for qubits. So this is something, now interestingly, it'll be great when we get to different, let's see. Let's look at how QSharp does it. Here, it'll be really, really interesting to see how those other languages, how they create, like for example, you have input 1, input 2, input 3. Here they're setting 3 qubits. I can see that here. Input 1. Interestingly, here this would be a register. If I were to put it back to the QC engine, it would be a register. But I would love to see in the other languages a register where they're adding different qubits. Like here, I know for a fact that if I were to do, if I set, let's say I set 4 qubits and I add 2 here, it's gonna show.
Can I ask you a question really quick? Do you know what binary
give me 1 second. Give me 1 second. So by doing this register here has 2 qubits, and these other ones only have 1. That's what I can say from the quantum programming perspective. Like the register seems to be a container for qubits.
Okay, thank you.
By all means, Daniel, my man.
I was just going to ask Danica if she understood what binary was.
It's 0 and 1, right?
Yeah.
Yeah.
So when we do that in a PC, right? We have a bunch of bits that are lined up, next to each other. And so being abstract, a register is just a set of those bits that are a contiguous set of bits.
Okay.
In this set, it's a contiguous set of qubits.
Okay. Thank you both. I really appreciate your coaching and not looking down on that question. I started blushing when I asked that question because it's such a beginner one to ask. But I really appreciate the coaching.
And I appreciate this because I will admit that when you read this chapter 3, 4, 5 times, you are just so entrenched with the syntax that you don't really think about what is it? So for example, if you were to ask me what is had, thank God last week we talked about it, but I know what it does. I can fully describe what it does, but describing fully what it is, that's a different story. You know? So that being said, let us get into the single qubit operation. And for that, I also created a couple of simple code for us. So first, let's talk about the single qubit operations. We have not, had, and phase, but the key to the that's my perspective. The key to the single qubit operations in a qubit register, and I will visually express what it means by single qubit operation. The key is to identify the qubit operator pairs, then to perform the operation. Okay? So keep that in mind, and we're going to go straight to the code and use the circuit and also the supplementation to actually see what that means. So I'm going to load my first code with not. Now I have a question. Does everyone have an idea that what the not operator does? Okay, just in case for those who would like a refresher or would just like to hear the sound of my voice, the not operator is basically based on which qubit it's being performed on. It switches. Is that what it does? It switches. Would you say that's what it does, Jeremy or Lynn? It switches. I don't want to use the word swap because there is an operation for it. So I'm trying not to use that expression. So let's run this program quickly. Perfect. So first, like always, we have to set how many qubits we're going to use. Here we have one register. And in this register here, as you can tell in this line of code, I've added 3 qubits in this line of code. That name was very boring. Register. Okay. Perfect. So we've set all the registers to start with 1. And then the first thing I do is to put in superposition just one of the qubits. And here I chose, the way you do it here with the JavaScript is QC had 4. Now, why 4? 4 is basically the equivalent, the binary equivalent. If I wanted to put the first qubit in superposition, I would put 1. So it's here. If I wanted to put the second qubit in superposition, I would put 2. Now let's say we have 6 qubits, and we have 6 here. If I wanted to put the, interesting, let's do this. If I wanted to put this qubit here, I would simply have QC that had 10. Please do not humiliate me in public. 8. QC that 8. What? See, let me try.
Gerard, can I interject here?
Please do.
So the notation, the 0x10, that's actually a hexadecimal number. So that's actually 16 decimal. What I found is you could actually, in the HAD, you could put 0x10 and it will show exactly what's on the screen. So I was using
you just
the hex notation to line
of
up.
the 2 power. Thank you so much. So here for this, 2 power, 1, 2, 3, 4, 5 power. Thank you. So here we have this. This is the not, and we have 1 single qubit operation on the first. Now let's go through this and see what happens. But first, let's just do it with 3 qubits. I think 3 is enough. Okay. So right now, we start. Now, we have the third qubit in superposition. And then now we have the knot on the first qubit. Perfect. And you read it. Now, the real question is, what actually happens? What happens after we perform the knot when the knot is performed on the first qubit, the 0 multiplied by 1 qubit? So from my understanding, the way I see it, which is, I think, pretty cool, it's every n pair will swap. So when I see this here, this is the 1. So I have this pair 1, 2, 1, 2, 1, 2, 1, 2. So this means that from that logic, this will come here, this will stay the same, this will come here, and this will stay the same. So what I use this idea, operator pair. You choose a pair, a quantum, the operator pair. For me, it's a group of circle paired with the circle separated by the n value. What do I mean by this? Since the operation is done here, so you start here, this is the first pair, second pair, third pair, and fourth pair. Sorry about that. So which means, let's say if we had, let's say we put the second qubit in superposition. Start here. So what would happen? So this is the first pair, second pair, third pair, fourth pair. So I'm expecting this to come here, this to come here, and those to stay the same. That's what I'm expecting. Perfect. Now we can even be a little bit more adventurous. You know, us developers, we love the adventure. So what we can do, let's look at my code examples. Perfect. We can, just to play with the knots, we can also use the phase, which is the idea of using the angles which those lines denote. So for example, here you have QC phase 90 degrees, and here too, which basically corresponds to this one here. So we're gonna have this one being in superposition and this one having the phase, but we're gonna use the same system. So superposition. Now you have the phase happening here, meaning some qubits are gonna anchor the phase and others are not. So the question is, why is it that it's only this one that anchored the phase, or that you can see anchoring the phase? Do you have any idea? No suggestions? Okay, Lynn does, but Lynn is on timeout because she's read it 3 times, so someone else needs to. Sorry, Lynn, I apologize.
Sure, could you say your question again?
So here, let me start again, if you don't mind. So we put the second qubit in the Lynn register into superposition. As you can see here, this started superposition, and then we performed the phase operator, and the phase operator was 90 degrees, meaning the 1 are going to shift 90 degrees. But then with the single qubit operator, only specific qubit circles here are gonna turn. And here, if you look at these, only 1 will turn. Why is it that it's only this one turning? Do we have an idea?
It's because the other ones are blank, so they can't rotate.
Say it again.
The other circles that are zeros can't rotate.
Perfect. So this leaves us only with those 4. So why is it that it's only this one turning and not this one? Well, why is it that it's only this one turning, not this one?
Well, the phase operation is relative to the one it's tied to, right? I mean, if you were doing a phase on, I'm just remembering back to chapter 1 or 2 when we first learned about it. It said it's relative to the one next to it. So they're not both going to turn, only one is going to turn. And since and since you're on the second qubit, you're off by 2. I'm not describing that.
Exactly. There is an interval. So the way I understand it, and hopefully this logic holds true all the way to the end of the book, here, since we are doing the phase on the second qubit, this first pair is out of the question. And you have this pair being in the question. Now, this is the only one that's a 1, and this one will turn. Now, we can make things more interesting and have actually let's do it. Let's make it even more interesting. Let's put the whole thing in superposition. As you can tell here, different angles. Now here you have the phase operation applied to the second qubit. So based on our logic, those 2 pairs not, this 2 pair yes, this 2 pair not, this 2 pair yes. So let's see. Same thing really. Okay. So let's see. So I'm expecting the phase to occur here and at the last one. That's what I'm expecting. Perfect. So just using Matthew's logic, thank you again for helping me, allowing me to steal it. So because it's 2, the second qubit, you are able to use an interval and then use this one. Now, interestingly, let's say if we were to do it with 4, with the third qubit. Wow, that's a big one. What do you think, which of the circles do you think would turn? We've already talked about that interval. Which circles do you think would turn? Before I click on this.
It'll be the last 4.
The last 4. Okay. Daniel has spoken. Anyone against Daniel? No? We believe in Daniel. And Daniel was right. Exactly. So you take, it's this interesting interval that's happening here. Now, we have a knot happening on the first qubit. What does that mean? Which of those will shift and which of those will basically not shift? Anyone would like to try? Nuri, my good sir, would you like to venture a guess?
Well, isn't a knot on the adjacent, like pair?
Yes.
So if it's pair, then the knots will swap in pairwise, the 0, 1, the 2, 3, the 4, 5, and the 6, 7.
You got it, my friend. You got it. Even if I were to turn here, it's those 2 here. Now, let's say we want to be more tricky. We did 2. It would be every 2. Those shifted and those 2 shifted, as you can tell. See that? This shifted here and this shifted there.
So this is the knot. I'm wondering though if you can take 1/2 slide before. Why did if the rotation, he always said start from dead center from 12 o'clock, and then 90 degrees will be 9 o'clock, will be leftwise counterclockwise. So why did both of the items in the pair shift instead of just one of them, and they're not in 90 degrees to each other?
So let's go back. So here we have all of our qubits notation.
Yeah.
We applied this. This is what we're expecting, right? We're expecting.
Well, I'm expecting that those pairs would have been the one targeted. My question is, before they started, where were they? They were at. They were at top and bottom at 6 o'clock and 12.
You know, I can tell you one
But
thing.
on the pair, the chapter previously said, hey, we don't actually touch the left-hand side, just the right-hand side. We rotate because it's phase relative. Yet here they seem to be shifting, drawing both.
So
Daniel, go ahead.
So the difference is with a 1, with 1 qubit, that is true. With 3 qubits, see, this is where we get back to binary, right? So if the phase is on the 4, then it's only going to shift on the circles where the 4 would be active, right? So in 0, 1, 2, 3, the third bit representing 4 is never active. So 4, 5, 6, and 7, it is. So that's why only the last 4 are affected.
Right. And my wonderment is, now that we decided which circles are target to be redrawn, why would the sticks in them, which have started at noon and 6 and noon and 6, right? Why would they not follow the rule of single bits that says only rotate them counterclockwise by the degree for
let's check something. So counterclockwise, this would be here and this would get there. That would be, let's go again. That's exactly what's happening.
Oh, so it's doing relative to their bit
to their
pair
position.
In the zeros in what the ones that didn't rotate. It keeps them fixed and got it.
So
Applies
here
relative
it
to
went straight to our 9.
Yeah,
and
that explains
it went
great.
straight to our 3. I believe that's what it is.
Yeah, I see that. Okay,
Thank
awesome.
you for that.
You.
I appreciate
That's
it.
great.
Thank you, my good sir. And then at the end, of course, we can read. And guess what? They're all 1. Perfect. Would you like to have another example of some single qubit operation? There's something I'd like to try by itself. So here we have a situation where we put all of our qubits in superposition. If we only put 1 qubit in superposition, the 2. And then we apply the phase here. Now, interesting, remember the phase works when it comes to, like this is the 3rd qubit, and there is an interval of 4 that needs to happen. So when we do this here, do we expect any of them to actually flip? Or not flip, do we expect any of the angles to change? No, we don't. Because those ones are here, but the targeted pairs are those last ones. Now we're doing a knot, meaning that the first 4 pair are paired with the last one. So we're expecting maybe the situation where this shifts over there. Is that what we're expecting? Or not? That is what we are expecting exactly. And then reading all 1s. I think this is one aspect of quantum computing that is very fascinating to me, because what it does, it raises questions. You know, as classical programmers, if you want to call it ourselves that, I never worry about things like garbage collection. Now I don't worry about garbage collection. I don't worry about what the bits are doing. I simply worry about a good algorithm, a good design pattern, and making sure that there's a lot of things are decoupled. But here, we're getting to a point where we need to understand how qubits work with each other in one register, and eventually how one operation in one qubit works with the whole register, and eventually how operations that affect many qubits will work. And what I'm very excited about is understanding how does it affect performance? How does it affect the power of quantum programming? Why knowing how those qubits and the circles that are targeted, how does it enable us to really harness this power? So these are more questions and subject of excitement for the future as we keep on going and understanding why we have to go through this lovely torture. That being said, do we want to continue or do you have more questions?
Jared, I've got another basic question for you. If you could flip back to the previous screen.
By all means.
So as we look at the register, it's got 0 by 1, 0 by 2, 0 by 4, and it'll keep going up the more qubits we add. But why is the numbering like that? Like, why does it go 1, 2, 4? And I know that it's exponential, and I think it has something to do with the 2 to the n. But is that something you could share guidance on?
So in the book, they talk about this labeling being the binary equivalent of the qubit. So I would assume that the first one is 1, 2 multiplied by 2 multiplied by 0 is 1, 2 multiplied by 1 is 2 power to 1 is 2, 2 power to 4 is Gerard. 2 power to 2 is 4. And then of course, when you get further down the line, we do realize that there is something happening that I don't fully understand yet. And Jeremy, you did mention things get into hexadecimal, right? Because when we have 4 qubits, let's do this. When we have 4 qubits, what just happened here? Oh, I didn't set 4. Right. When we have 4 qubits, it goes to 8, which is 2 power to 3. This is here 2 power to 0, 2 power to 1, 2 power to 2, 2 power to 3. Now, when we get to 5 or 6 qubits, here it shows 10, 20. But then Jeremy, in his humanly infinite wisdom, reminded us that this is hexadecimal, right, Jeremy?
Yeah, so it's hexadecimal. And if you're not familiar with hexadecimal, it goes, binary is base 2 and decimal is base 10. Hexadecimal is actually base 16. So if you were to count in hexadecimal, you'd actually go 8, 9, A, B, C, D, E, F, 10, or more properly 1, 0. So 1, 0 in hexadecimal is actually 16 in decimal, which would be 2 to the power of, where are we? 4, 5?
I think
5.
2 to the power of 5 is 16. And then since 10 is, or 1, 0 in hexadecimal is 16, 2, 0 in hexadecimal would be 32. Is that right? Did I get that right? And so
5 is 32, 2 to the 4 is 16.
Yeah.
So
5 is 32. So yeah, it's kind of confusing because in order to kind of dig in to understand these examples, you need to understand hexadecimal, which is, this lovely notation, as well as binary, since our bits come out in ways that produce decimal values. And so the numbering systems, I would definitely say look into the numbering systems a little more. In the little repo that I did, that I put up on GitHub, one of the things I have is just like, okay, here's the binary values and the decimal values from 0 to 16, I think is what I did, just so that I could have the bits in my brain. So I think I should probably add hex to that as well, so that there's just a nice little chart.
Mhm.
So I think the other thing, like that they're not in order, right? There's not a 3. So 3 is represented by 0x1 being enabled and 0x2 being enabled. So it's done like this because now we can represent every number in ones and zeros without having to have like a special 3, right? So it's just 0, 1 is 1, 1, 0 is 2, and 1, 1 is 3. If that makes any sense.
Yeah, this is helpful. Thank you all.
Okay.
You're welcome. So here, we recently, just right now, we had a wonderful adventure in the single qubit operation in a register, meaning we are able to see how one qubit in being operated on affects the whole register. For example, here, you had just one qubit having a phase of 90 degrees, as you can see here, and also a knot. You are able to see how it affects the whole operation. Now, we are going to head into the multi-qubit operation. 1 second. And of course, by multi-qubit operation, I mean the ones that require more than one qubit to operate on. First, I think we're going to start with one of the easiest ones to comprehend, the C naught. Then we'll get into C phase, we'll talk about swap, and then of course the CC naught, which is very interesting, but apparently the CC naught is one of the most powerful operators that we can use here. So first, let's see, what did I do here? Now at a small loss. Okay, if you don't mind, let's go straight to the code. And because, for some reason, this is not registering with what I have in mind, but let's head to the code and we will explore how multiple qubit operation affects a register. And for that to happen, we're going to start with C naught. And just like the annoying teacher, I'm going to ask you, how do we start the operations? I'll start with Danica. What is the first thing we do?
Is it qc.reset?
Perfect. And what is that again? What does it do?
Doesn't it initialize your qubits?
Excuse me?
Initialize your qubits?
Lovely. So let's initialize 3 qubits. So right now, I'd like to create 2 registers. How do I do that, Daniel?
Variable A equals qint dot new, I think, and then parenthesis, how many qubits you want.
How many qubits do you want? Oh, I already put 2.
And then a name.
A name. Thank you, Daniel. Okay, since this would be cheating if I were to ask someone else for the same thing, I'll just keep someone else on their toes for the next question. So we initialize 3 qubits. It's interesting because I think I prefer saying we allocate, or because there's another thing that we do where we write a value. So for example, let me show you. there's also this operation where we write a value, either 0 or 1. So I don't know here, this is where we initialize it or we allocate it. I'm not quite sure if there's a big difference, but this is necessary for all the operations. So first, let's do this. Before we are able to use any qubit or play with them, it's always great to put the qubit into the powerful state of superposition. And we do this by either putting the whole registry in superposition or just one qubit. So first I can do, if I do a.had, I put the whole registry in superposition, both of it. So we could do that. Or if I do a.had that in 1 inside, I only put the first one. If I do 2, I put the second one. So this is a little trick for you guys.
And if you did 3, it would do both again.
Check. Ta-da! Which is basically QC had. Not Gerard. Okay. So now we've put those two into superposition, but this one is not in superposition. Something we can do now is use the C0. And how do we use the C0? C0. We use 1.
Don't you say A dot C not B or B dot C not A?
Good question. Good question. We can try that. I already have something in mind, but A dot C not A. Oh, B, sorry. Are you a developer, Nuru?
Sure.
Okay, because you have an amazing curiosity. So let's do QC read at the end and see what happens. So right now we have AC, A, C naught B is like the first qubit and the last qubit having this, being entangled right now. Like all of them are entangled. But then what truly happens here? So what we have, the first 4 circles. So now we have the not. Actually, yeah. So we have the not notation. What do you think happens here? Because here we have this C naught, the last one. What do you think happens? We both know that the C naught, what it does, it flips or it switches. Now the question is, which of these are going to be switched? And how do we do that? Any ideas so far?
I'm game. So
who's that? Jeremy? Okay,
it was me.
Let's have Jeremy be last resort.
So, I'm a last resort.
No, I have to excuse another chance.
Well, the C naught is a conditional knot, so it will, in this case, it'll do the knot on that first qubit based on the state of the third one. So if the third one is 0, it will not do the knot. If the third qubit is 1, then it will do the knot.
So here, if this first qubit, so basically it's saying not you, but it'll start here, right? It'll start here, and then it will do whichever this is doing, or is it the opposite?
Well, in this case, the conditional is not in superposition and it's a 0, so it shouldn't do anything.
Exactly. Exactly. So basically, nothing is happening here. There's
Well, I don't think that's fair to say nothing's happening. Something is
happening, but not very obvious, because yes, it's on the superposition. Now let's do something else. By the way, thank you very much, Jeremy. Thank you so much. Let's put everything in superposition. If we were to do QC had, we would put, I believe we would put everything in superposition. Now, does someone else would like to venture what would happen here? Because we do know that this is the not. It would be to add like a phase to just one. Let's say we're to add a phase in, it should be the Hogby phase. Let's do QC phase. I believe this is 4. What I want.
This is where I felt like the book was lacking in documentation as to what the arguments are supposed to be. And like what order. It was like, so now what? Right, so right now you're changing it 2 degrees. But you want to change it, or you probably want to change it 90 degrees on the second bit, right?
Yes. Perfect. Here, what would happen is exactly what we talked before. This is a little bit more interesting. The C0 uses the first, I would say this as a condition, and then the not. Now let's add a little bit. Let's make it more interesting. So we did A, C0, B. We can also do. I like QC, C0, 1. So here. Now, what do you think happens using the second qubit as the condition? So here we have a little hint. You have those 2 and those 2. What do you think happens after? Nothing, because they're the same. Conditions are here. If we were to change this, let's do 4. Same thing. Well, actually, let's reverse it. Now, if we're to do this, having the condition being on the first one, what would happen now? Remember, this is more like not, yes, not, yes, not, yes. What would happen? Which of these would switch?
So it's conditional on the single bit. So it's only going to matter for 1, 3, 5, and 7. And then it's going to not the 4th bit. So the 1 would become a 5, and the 3 would become a 7, and the other way around.
1, 3, 5, 7. The 1 would become a 5.
Right.
And what? Which other one?
1 and 5, 3 and 7.
3 and 7.
Because we're swapping 4, so it's going to change by 4, right? 1 and 5 are separated by 4.
And again, part of that logic is the fact that we're using the C0, meaning the first condition, this one is out, this one is in, this one is out, this one is in, this one is out, this one is in, this one is out. Now, in terms of pairs, we have this all the way to 5, 2, is that? 4 to 5, the 2 is out, so the other one is the 7. Are you ready? Perfect. This is an interesting example of how multiple qubit operation affects the whole register. And it also almost follows the same system as the 1 qubit operation. The only difference is you get to use in your calculation two variables. For example, the fact that here, the condition like not, yes, and then based on that, you do the swap with this interval to 5, 3 to 7.
Yeah, I really like, Daniel, the way you explained it, because from a totally plumbing or mechanical perspective, there are 2 questions to answer. 1, which one is the controlling bit? Well, that's the small dot.
Mm-hmm.
And second, which of the output binary
Circle.
bits that actually signify the number, those subscripts, so which of the subscripts has that bit on, answers the second question. And then based on the subscript of the original qubit on the lines on the staff above, is it interleaving 1, 2, or 3, or n? That's what's the interleave. So it's really what's the control bit, what's the interleave, and that gets you into the bottom zone to pick the right circles.
You know, as you were talking about this system, it simply requires doing it over and over until it becomes second nature. Right now, we are think about the days when we just see this and automatically in our mind, we know which one are changing. Think about that day. That day, I'm going to be excited. But of course, before we get to this day, which is our version of running, we have to learn how to crawl. And to crawl here, it's no, 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 yes, and then this one, interval 4, 5, not this one, 7. In fact, we can get into another one right now. I believe we just did. We can also do the Q phase. Okay, that would be a wonderful one. The C phase, I'm sorry. C phase is almost the same operator, but of the same system, but of course, using this notation and changing the angle. So let us do this. We can actually keep the same code here. Let's just add a Q phase system. So let's see, how would you do the Q phase? You see how you did the C0 at this point? We use the 0, 4 as a control and the 0, 1, no, the 0, 4 as the one we're actually using the intervals, and the 1 as a control. It's almost the same thing with the Q phase. Difference is 45 degrees. We're going to use the 2 as the intervals, and we're going to use the 1 as the control. By the time you get there, you know something is gonna, you know, let's do 90 degrees. Because it might be easier. By the time we get there,
Comma. Missing a comma.
oh, thank you. By the time we get there, we know what's going to happen. Now that we know that the first one is the control, and
No,
the second one is the interval.
no, you're not doing a C phase. You're just doing a phase. Right? So in this one, it's rotating both
Yeah, you're right.
0x1 and 0x2.
You're right. You're right. Let me look for, what is the code for C phase? Oh. Shit. I think that's probably where I got. Do you remember the syntax for the C phase?
I don't remember him sharing the syntax.
So I pasted into the chat, there's actually a cheat sheet for the QC engine. And so you can look at that, and there is a QC phase where you do give it 3 parameters.
Oh, yes. There's an output. There needs to be an output. You're very right. The QC phase requires an output, an output register.
Yeah, there isn't a C phase separate operator.
Yeah, that is very, very true. Thank you for that. I totally forgot about that.
You're actually doing it. A phase, a QC dot phase with 3 arguments.
Yeah,
is giving you the arguments are angle, comma, control qubit, comma, target qubit.
But C phase isn't, can you try running it?
No, it's not doing what it's supposed to do, or it's not showing the actual way. Let's see.
So I'm not seeing C phase on the list either. So, but I'm confused how to make it work, because when it was just phase, there wasn't a conditional there.
Mm-hmm.
well, I think the notation, I'll need to refer back to the book because my memory is not great. But I think it said because of the way that C phase operates, the notation is really just the phase change on both. Yeah, so if I look at page 50 and 51, it actually shows that because of the way it operates and rotates the values, that the control versus the not, the control versus the target doesn't really matter as far as the output is concerned. So the notation is having the phase on both of those qubits.
So I do see that there's, for C phase, there's a, I need to go back to the material and really see how to do this. I did put a phase of 180 degrees, and it does correspond to this, which is similar to what they have in the book. So maybe a phase of I know that the phase of 180 degrees is what they call the CZ. So this would be a CZ. I don't know what would be a C phase.
Yeah, I think if you change your 180 to a 90, then it'll go back to that other notation that shows the phase on both of those qubits.
Anything but 180, yeah.
Yeah.
Okay. So basically this is a C phase.
Yes, it is.
Okay. So guys, we were right all along. Right all along. This is a C phase.
There's another little trick that I've been playing with. JavaScript does not require you to say numbers in hexadecimal, which is sometimes difficult to decode in your hand. Oh, 7, that's the 3 bits. Oh, 8, no, that's the 4th bit, but starting at 0. So you can basically set 0B and then 1 0 1 1 0 whatever. And that is binary notation. And it's a little easier because it aligns the bits. It does 1 0, if you're using a fixed width font, at least from the QC engine perspective, it's easy to see which bits you're targeting. Because sometimes the number 2 means the second one, or actually the third one with 0 index. And sometimes it means 2, as in the second bit is on. And it's just kind of awful to read, this kind of try to understand what the number now represents. So I find it easier when specifying bits to use the binary notation.
I will be very interested in reading your thoughts on this. Maybe you can drop that in the chat. That being said, it is 6:15, and I know that in my excitement, I've actually run through our time. If we don't mind, do you think it would be too much if next week I finish this chapter in 15 minutes?
I think that would probably be good, because when we get to the part about entanglement, I think is going to be key to a lot of the things moving forward. So I think definitely next week we should start with the bell pair, and so we can get a good handle of what that is as we move on.
Wonderful.
Will there be time for a chapter 4? I mean, there's kind of still a lot.
Yeah, there is a lot. So first of all, is there anyone who wants to volunteer for chapter 4 at this point? Yeah, I heard silence.
I don't mind volunteering for a later chapter. This is Matt, but this coming week, I've got 2 birthdays for kids, so my prep time is going to be almost nothing. So the following week, I'm happy.
I can probably do the next chapter, but how does it put us into next week?
Yeah, next week, I think
it makes a lot of sense to
next week is maybe a catch-up.
But I don't think it will behoove us to then start a half chapter. Maybe we can extend that and just say we'll finish covering this chapter next time, and then open up to questions, experiments, things, and then defer the next chapter to the after.
Yeah, we'll do a catch-up week next week, because I know last week we also left some things about the last exercise in chapter 2 as kind of requiring further discussion. So yeah, next week we'll call it a catch-up week. So we'll finish up chapter 3, and then based on that, go back and see if there are things that we want to revisit on chapter 2. And I'm glad to lead that discussion, and then we could talk about chapter 4 for the following week. Does that sound good?
Thank you very much. Thank you, everyone, for being in this presentation. Thank you for going through the problems, the coding with me. I appreciate it.
Yeah, great. Thank you very much for going through this, Gerard. We really appreciate it.
Yeah, thanks.
By all means.
Thank you.